This is a screencast of Chapter 11 problems. We went over these pretty detailed today, which is, I think, January 24th. It's a Thursday. And um, I think that was helpful with the way we went through them. But I know there were a lot of people absent. So if you were absent, I would strongly encourage you to look at this again. We've got a test February 1st, sort of staring down at us about a lot of these things. At any rate, for problem 4, the key here was understanding that what you were doing was converting gravitational potential energy into electrical energy. So what I have to do is I have to figure out the rate at which this energy is changing. So it said that 690 cubic meters of water per second were passing through the dam. Have to know the density of water to figure out how much mass that is. So that's 690,000 kilograms per second. Multiply that by G times delta H, which is how much it's falling. And that tells me how many joules of potential energy is the input. It said that 90% of that was actually captured by the turbines to create electrical energy. So I multiplied that by 0.9 to get my answer. So 1.34 times 10 to the 9th watts, or 1,340 megawatts. Megawatt is a typical unit of power when we're thinking about power plants and things like that. So 5 was a light bulb. It said an LED used 1 watt, but it was 20% efficient. So only 0.2 watts of light were output. And it said that if you needed 1.6 watts of visible light, how many bulbs would you need? Well, that's 8 bulbs. Well, then to figure that out, if how much total power was needed to run those, 8 bulbs times 1 watt per bulb, 8 watts of power to run them. For P32, we've got 120 watts, which is 120 joules per second. So if we run those for an hour, was asking about how much heat was produced if a fan is on for that amount of time. Because eventually all the energy goes into heat. It's not like the air keeps moving within a room because of like friction with the air molecules. So that's 432,000 joules of heat. For P33, notice I put not relevant for this, but essentially this is, I was thinking about it like a heat engine, and a couple people in class talked to me about that. But this is first law of thermodynamics. This really would be delta U if we think about things like on your formula sheet. So it's delta U equals Q plus W. Your book uses delta E thermal. So we had 600 joules of heat input, 400 joules of work done by the system. So that's leaving. So you have a net gain of 200 joules. Therefore, this system would heat up overall. I asked a question in class about this, whereas if you had 600 joules of work done by the system, what would be the change in temperature? And it's 0. Even though you have heat coming in, you're doing work. And if those two are equal, you have no change in internal energy, and therefore no change in temperature. So for P34, we've got a constant temperature, so that says that it's isothermal. So therefore, work is positive if something's being compressed. Q is negative if heat flows out of the tank. They have to be the same magnitude if the internal energy doesn't change. So P35, if delta U is positive, the temperature would increase. We find that's true because it says we've got 20 joules of work being done on the system, 10 joules of heat being transferred from the system. So that's a net internal energy change of plus 10 joules. P34 was a little sneaky. I think most people rounded this to 20% and 5,000 joules. So basically, you have to realize that your hot and cold temperatures need to be converted to Kelvin. You can find your maximum efficiency using this. And so that was about 66.4%. But it also says that you only get 30% of the maximum efficiency out. So I multiplied that 0.664 times 0.3, and the overall efficiency, therefore, is going to be 19.9%. So if you have 1,000 joules of input, 19.9%, or pardon me, 1,000 joules of output, 19.9% efficiency, your input is a little over 5,000 joules. Again, you could round this to 5,000. For P43, Cold temperature was, again, 303 Kelvin, so I'm making sure I convert these automatically. Hot temperature is 573 Kelvin. Emax was 47%. The actual basically said you had a power plant with 700 megajoules per second, or megawatts of output, when the input was 2,000 megajoules per second. So that's 35%. So it makes sense that the actual efficiency was less than the theoretical maximum. For P52, this was looking to see if we violated first law or second law or no laws of thermodynamics. So what it is, I labeled these hot reservoir, cold reservoir, 600K and 300K, and what we knew about the energy flow there. And so in this case, the maximum efficiency with these two temperatures should be 50%. If we look at it, it shows us having 30 joules of work being done. Well, that's 60% efficient. So that violates the second law. So that is too efficient to be correct. And I can talk more about that if you want, since it relates to entropy. This second one has 10 joules going in, but a total of 7 plus 4, or 11 joules going out. That obviously violates the first law. For letter C, we have 30 joules coming in, 30 joules going out, so we're okay with the first law. 10 joules of work being done divided by 30 joules of input is an efficiency of 33%. Since the maximum is 50%, we're okay. So that one is no problem. For P64, you're asked to find the efficiency of this. You have 15 joules of heat exhausted and 10 joules of work done. So knowing that, I know that I have 25 joules of energy that's input. So the efficiency is what you get out over what you put in. So that's 10 over 25, that's 40%. To figure that out, essentially then, I'm working back to see with that efficiency what the theoretical temperature would be. So the cold temperature was given as 20 degrees Celsius, so it's 293 Kelvin. So if 40% equals 1 minus Tc over Th, and we know the Tc is 293 Kelvin, we can work that out mathematically and see that the Th must be 488 Kelvin, and I converted that to Celsius, so that's 215 Celsius. P66, if you have heat reservoir of 100 joules, work done is 50 joules, that's an efficiency of 50%. So that is possible if 50 joules is exhausted as waste heat. So the smallest ratio of temperatures of hot to cold would be 2 to 1. So thinking about the maximum efficiency of 50% is equal to that formula. So it's going to be 1 minus 0.5. 0.5 would be a 1 to 2 ratio of temperatures from cold to hot, or 2 to 1 from hot to cold. So hopefully you see the same patterns kind of over and over in terms of this. I think this is a part of the course you should be able to be pretty successful in. If you had trouble with this, think about what it was that was puzzling to you. Hopefully we went over that in class, and if you weren't in class, hopefully you can check with me.